Hey everybody, and welcome back to Algebra 2 Online. The plan for today is to just go through some of the kind of most important topics from Unit 5 here in review for the upcoming test. So let's just get into it. So write in factored form the equation of a negative polynomial that is degree 8 and has two double repeated roots, like double or repeated roots, and at least 3 imaginary roots. Okay? So, to do that, double roots, right, are ones where, like, you just have the same factor twice. So, I guess first off, too, we know it's got to be negative, so let's just do that. And then you could have, like, x plus 1, that factor twice, so that's one double root. Then you could have, like, x, minus 2, that's another double root. So that's 4 roots, right? And it's degree 8. So I say at least 3 imaginary roots, but we know we need to equal the degree 8. So there really has to be 4 imaginary roots. So, we just need 2 more that are imaginary. So you could do like x squared plus 1, right? That would be a quadratic factor that gives 2 imaginary roots. And then you could have another one like x squared plus, 2. And that would have imaginary roots, right? Here the roots would be plus or minus I, and then here the roots would be plus or minus root 2I. Not that you need that for the problem, but then down here it just says to roughly sketch what this polynomial might look like, right? So we know that with this factor, it's got a root at -1, that's a double root. And then with this factor, it's got a root at 1, 2. And so if it's double roots, right, those are the ones where it's going to come in and like touch the graph and then kind of bounce back. And I knew it was down here, right, because it was a negative degree 8 polynomial. And so if we could draw an arrow there, do this. Now we just need, so let's say that's what we had. This is 1, 2 roots, 3, 4 roots, and this could be understood as 5, 6, right? But we want 8 roots, right? So we should really do, just to be super clear, something like that, where it can't cross or touch the x-axis again, because then it would be real. But these basically are like your 2 unreal or imaginary roots, and these are your 4 imaginary roots, and these are your 4 real roots. So that is roughly what this thing could look like. All right. So another big part of this unit is just finding roots, and I want to make sure that you sort of think about the easiest way to do some of these. So a lot of times what I'm seeing some issues with is students don't always see kind of the nicest things to do. And the nice thing to do here, if you ever have a polynomial that's got a variable in every single term, you should absolutely, even before you try to think about other techniques, just go and take that x out of every term, right? And so now you have a much easier polynomial to solve. One root's going to be 0, right? Because if you plug in 0 here, you get 0. And then you just have a quadratic to solve, right? And actually, this quadratic is a really nice quadratic because it also factors. You could have x, plus 7 and minus 3. And then without even getting into techniques we learned in this unit, you know that 0 is a root, -7 is a root, and 3 is a root. This question also asks that you sketch what this graph could look like based on the roots and the leading coefficient. So we know it's positive, x cubed, and we got the roots. So, roughly speaking, got a root at 0, root at -7, root at 3, and we know it's positive, so it's going to start down here, and over time it's going to trend up to the right. So, just like you have positive slope goes uphill, right? This one has to trend up as you go over to the right and up and to the right. So the point of this problem is just to make sure that you see the easiest ways to do problems. And this is an example of one where the easiest way is just to factor, basically. You don't even need the techniques we learned in this. Probably the hardest way would be this. So I just wanted to show you this thing. So that last problem is a cubic, right? And there is actually such a thing as a cubic formula. This is kind of a funny meme to me. So me knowing the quadratic formula, right? Kind of reasonable. Everyone kind of knows that. And then the kid who knows the cubic formula, a very unreasonable sized instrument there. I don't know what that thing is, but the cubic formula is literally a formula that gives you all three roots to the cubic, to any cubic, of the form ax cubed plus bx squared plus cx plus d. And, so like in this, this problem from before, right, a is 1, b is 4, c is negative 21, and d is 0. And the crazy thing about the cubic formula is you actually, so this would give you just one of the roots, right? But we know we should get 3. And so there's actually versions, they look kind of like this, but just like the quadratic formula has like a plus and minus, there's basically some terms that are going to be negative, and you get some kind of different things that way. But technically this is like this general structure of the cubic formula. And you'll notice there's like a cube root here, and then inside of this cube root there's a square root, and there's a whole bunch of weird terms in here, squared, cubed. This line is just a continuation of that, so they're not separate things. This is all just to get one root. I'm not going to go through it, but there really is such a thing as a cubic formula. I just wanted to show you it, and this is just really part of the cubic formula. It would be like if someone wrote the quadratic formula as x equals negative b plus the square root of b squared minus 4ac all over 2a. So the same way that this is part of the quadratic formula, this is part of the cubic formula. If you think that's bad, look at this. It's so small, you probably can't even read it. So this is a general x to the fourth, what we call a quartic, and believe it or not, there is such a thing as a quartic formula. This is actually all four roots that you would be getting from the quartic formula. Really, really, really hard for probably you to read it. This is truly like nested square roots and all sorts of messy things in here. There's a lot of roots. Actually, they're not just all square roots. There's fourth roots and different weird, messy things. So that kind of begs the question, does this just keep going? Can you keep finding a quintic root formula or something like that? But it turns out that no, you actually can't. The highest that you actually ever go is with these formulas is the quartic formula. It's actually been shown that you can't do it for the other ones. Actually, I just looked at that a little carefully. That's not a fourth root. That's those are cube roots. Not that it matters. I'm never going to ask you to do this thing. But yeah, that's actually a pretty famous problem in math that we basically can't get a closed form solution of the higher order polynomials. So you basically need techniques like we've seen to kind of get you started, and then do like reduction problems, and then you might use something like this. And there's other techniques out there in math that, like, if you need them, you'll use them. But honestly, you go far enough and eventually you just start using a computer to help you do a lot of this stuff. So just wanted to show you that because technically it is a thing, and it's kind of cool to see, I think. This is probably the most useful problem to make sure you know how to do for this unit. So the biggest part of what we do is learn these techniques for finding roots of higher order polynomials. And we've got 3 techniques: factor by grouping. We've got the U sub technique, and we've got the rational root theorem. And this is kind of your slowest, most tedious method. It's your guess and check thing, right? Where you kind of have an option for what a possible rational root would look like. And then you do like guess and check, literally, to see if it's a root. And then if it's a root, you do division and kind of reduce the problem and just keep going. And then you might have to do it 2 times or 3 times sometimes. These 2 were taught in the same lesson. This is the one that revolves around looking at the polynomial in terms of groups and hoping basically that you can like split it up into even-sized groups and pull out something from each group that leaves you with a common factor. U sub is the one that needs 3 terms, where you have the special pattern with the exponents, so it can turn into a quadratic. So this is the one where you might have like x to the 10th plus or minus x to the 5th plus or minus a number, and you could do a U sub problem there and just let like u equal x to the 5th. So what I want to do is just go through this big messy problem. We would need 5 roots, and just kind of show you how we might use these different techniques to do this thing. So honestly, the best way to do this one is actually first to do a factor by grouping problem and then do a U sub. But I think it's good to practice the hardest things. So I'm actually going to show you rational root theorem first, or like actually the only way I'm going to show you, and do it out that way, because I think it's the hardest technique and it's good to show you more examples of the hard one. But I want to at least have you see that you could do factor by grouping. So if you imagine grouping this in terms of 3 groups of 2, if you look at the ratio of these coefficients, 5 times 5 is 25, 26 times 5 is 130, 24 times 5 is 120, right? So the ratio is perfect for factor by grouping. So really the best way to do it is to just do factor by grouping, and a good practice on your own would be to try factor by grouping first and then see that you can get the same answer I'm about to get. But you might not see that, right, if you were in the midst of a test or something. So it's good to practice like rational root theorem, because I think it's the one that like we all know, and it's just sort of tedious, but we can always rely on it to help us, right? So in this problem, if I do my PQ thing, oops, that's supposed to be Q, PQ, P is the factors of 120, right? There's quite a few. So you could have 1 and 20, right? 2 and 60, 3 and 40, 4 and 30, 5 and 24, 6 and, oops, I don't want to write that yet. 6 and, what would it be? It'd be 20, right? And then 8 goes into that, 15, 10 and 12, and that's it, right? So 12, 15, where was I here? 8 and 15, 6 and 20, and then we'd have 24, 30, 40, 60, and 120. Whew. And then factors of P is nice because it's just, or sorry, for Q, q is just the factors of the first term. So it's just literally 1 and 5. And remember that you could always have plus and minus. So I picked this one because it's an example of one where, we talked about how to use our calculator to help us get started. Now, again, in this problem, you really should do factor by grouping. But if I was doing rational root theorem, I'm not going to go and check all these different roots, right? There's a ton there. There's I don't even want to count how many. You count up all these numbers and then, times by 2 for this, but then double it 'cause plus and minus. So you would just go to your calculator and you would use the, so basically use the zero button on your calculator, which I showed in a previous video. And if you do that, when you graph this thing, you would see that 5 is a root. And then find 5 is a root. And then from there, that's where you would switch into a reduction problem. So you have 5 as a root, and then you've got, you want to bring this down to an x to the 4th, or a quartic. So we have 5, negative 25, negative 26, 130, negative 24, 120. Bring that down. Multiply here, we get 25. Add those, you get 0. That's a 0 then. Negative 26. Negative 26 times 5 is negative 130, which is nice because that adds to 0. Then you can bring that down. And let's see, is 5 times 24 120? Yeah, it's negative 120, so that really does cancel. So remember, this is your remainder. That's supposed to say the word remainder, and it doesn't look that way. So now you have 5x to the 4th, right, minus 26x squared minus 24 equals 0. And so far we've got one root. We still need 4 more, right? But at this point, we have a nice setup for u sub, right? If we do u equals x squared, u squared will be x to the 4th, right? So if I switch my problem to u, I get 5u squared minus 26u minus 24 equals 0. And I would just do quadratic formula because the 5 in the front is kind of a big annoying number to try to factor. So I would just go and do quadratic formula. Remember, it's for u though, not for x. So if I do a u quadratic formula, I'm going to get 26 plus or minus 26 squared minus 4a c all over 2a. And I mean, that's something we've done for a long time. I'm going to let you fill in the blanks there a little bit. You get 6 and negative 4/5 from that thing. And then you're not done because you just found u, right? So if, so we're going to go right up here. If u is 6, then that means that x squared is 6. So then x is plus or minus root 6. And then likewise, if u is negative 4/5, then x squared is negative 4/5, right? So x is, we'll just do plus or minus square root of negative 4/5, and then I was just going to simplify it a little bit, which is why I paused. Square root of 4 is nice, right? So we can do plus or minus 2 square root 1/5, and then you have a negative in the root, so stick an I on that thing. And you're done. So we have 2 more roots here, and then 2 more here. So we have 1 that we would find with a calculator. 2 more you'd find this way. 4 more you'd really find with substitution, but 2 more from that little part, and then 2 more from that part. But really, again, and this is good practice and you should try it, try to do factor by grouping and see if you can get the same answer. Rational root theorem is the hardest way, but it's also like the most mindless way because you just, use a calculator, find a root. do your synthetic division. It's like, it doesn't require as much trickery sometimes as factor by grouping does.